Hi, in this video we are about to see the finding C by A ratio and packing factor for HCP. First let us consider a HCP structure which consists of an atom in this manner, then surrounded by 6 atoms. Now, connecting all centers of the atoms leads to a hexagonal shape. Well, so this is a hexagonal cross-packed structure, and in that, say, ceiling or floor level consists of such atoms. Now, considering the same structure in a side view, say this is the top view of the atoms, and side view may be drawn in this manner. Say the side view bottom surface is shown here. Now the center of atom is here, say O, and this A, and this is B. Now connecting all these points leads to ABO. The same side view, this is the side view, this is the top view. Point O is here, and point A is here, and point B is here. Okay, fine. Now creating a normal from the point A towards this BO line, and similarly another normal from O to AB. So these normal drawns are A dash and say O dash. Now these points A, B, O and other things are separately drawn here. Say this is A and this is B and this is O, this is A dash and this is O dash, and this happens to be an equilateral triangle, and the angle is 60 degrees in between these, and here it is 30 degrees, and in this case cos 30 degrees or cos theta cos 30 degrees is equal to root 3 by 2 from the figure. It is the right angle triangle A dash B, so that happens to be the right angle triangle A dash and B. So cos theta, adjacent side, so here is 30 degrees, so adjacent side is A dash divided by hypotenuse side, it is AB. The AB here, same distance is here you could find AB is a 2R. See, I am marking here it is 2R. This is a 1R, another radius here 2R, so which is equal to the lattice constant A. So 2R is equal to A. R is the atomic radius, A is lattice constant, so R is equal to A by 2. Say this is equation small a, R is equal to A by 2. Now with this detail we can put here as AB distance is small a, so A dash is a small a, say A dash divided by small a is cos 30 degrees. Now A dash may be written as A into root 3 by 2. Root 3 by 2. So this happens to be the same value also for the O dash normal. A dash we have calculated, and this is equal to O dash. So this we can keep it as equation number B, small b. Okay, now from the figure we can find another detail, that is A dash normal and O dash intersect at the point X. Now distance AX may be written as 2/3 the length of A dash, since it is a geometrical figure, and that happens to be AX is equal to 2/3 the length of A dash. So AX may be written as 2/3 the length of A dash. A dash we have already written as A root 3 by 2. So that will be simplified as A by root 3. So AX is equal to A by root 3. Say this is equation C. Okay. Now coming back to the figure, here you could find A, B, O we have taken, and we have measured all these AX, A dash, O dash, R is equal to A by 2, all these information we have captured. Now considering the entire dimension of the HCP structure, say the entire length of the unit cell is C, and 3 atoms are placed at the middle, which is at a distance of C by 2. The entire length is C and half of this distance is C by 2. The entire length is C, half of this is C by 2. Now the middle layer atom, one of the middle layer atoms, say point C, center of that atom is C is considered. A normal drawn from the center of that atom comes and hits the point X. So I put it here. This figure we can find this is all these A, B, O are at the ground floor. The first floor atom or middle layer atom C is considered, and its center point when it is projected downwards comes and hits the point X. This height is C by 2. This height is C by 2, and this AX value we have calculated. Now considering the points A and C, I put the figure here. Say this is atom A and the point A is here, and atom C, say which is happens to be a middle layer atom, point C. From A to C distance is 2r is equal to small a, lattice constant, and the normal drawn to the projection from the point C comes and hits the point X. So all these A, X and C creates the right angle triangle, and this AX distance we have calculated as A by root 3, and this is A, this distance is small a, and this is C by 2. This is C by 2, this is point X. Okay. Now this is the right angle triangle that we are talking about. This is point X, and this is C, and this is A. Okay. Now assuming that this XC or C by 2 height is not known, then this is a known value A, and this is A by root 3. Okay, so we can find CX by taking this hypotenuse is squared, A square minus this side, AC square minus AX square gives CX square. So CX square is equal to A square minus this side square, AX square, A square by 3. So that is leading to 3A square minus A square by 3. So 2A square by 3. That is CX square. To find CX, root 2 into A by root 3. So that is CX. Say this is our equation number D. And we have said that this is equal to C by 2. This CX distance is C by 2. So this, whatever we have found as equation number D is equal to C by 2. Our interest is to find the C by A ratio. So what I do, I take C and A alone in one side. C by A is equal to C by A used to be calculated C by A. So C by A I have taken. A, say A, C A is here, C is here. C by A is equal to root 2 into 2 divided by 3, root 3. So square root of 8 by 3, and the value comes to 1.633. So C by A ratio is calculated from this. and we are about to use this information for finding packing fraction. Okay, I am proceeding for the packing fraction. Packing fraction. Packing fraction is obtained by volume of the atoms inside the unit cell divided by the volume of the unit cell, capital V. So in this case, there are some 6 atoms inside the unit cell. Here you could see 1.5 atoms at the floor level. Similarly at the top also 1.5 atoms, middle layer some 3 atoms. So put together 6 atoms. So 6 into 4 by 3 pi r cube divided by volume of the unit cell. The volume of the unit cell is obtained by half BH into 6 into C. That is, half BH is the area of one triangle. Say I am shading a portion here. Say this is a area of one triangle. Similarly, there are some 6 triangles here. Connecting each atom center towards the center of the atom center, it creates 6 triangles. So half BH into 6 and the base area multiplied with the height of the unit cell C. That gives the volume of the unit cell. Okay. Now this B base is already we have seen that base is AB. Say this is base. There is A, small a, lattice constant. This height H, O dash, that also we have already calculated. O dash, A root 3 by 2. So I use all this information in the packing factor formula. 6 into 4 divided by 3 into 3.14 into R cube. Instead of R cube, I can use as A by 2 is R. So A cube by 8. The rest of the things also I am substituting. 1 by 2 into B. This base area, base length is small a and height is A dash or O dash is the height. That is A by root 3. A into root 3 by 2 into 8. So you could see here it is now left out with these terms. There is A cube and A. So here denominator A square, here it is A cube. So remaining things are A. And in the denominator, one C is left out. So rest of them are simply numerical values. And when I simplified the equation, say 2 and here the yes 2 and 2 gets simplified here as 4, then these 2 and other 2 will go to the numerator. So I write the remaining things. 2 into 4 into 3.14 into this 2 into 2 into A root 3 into 4. Then C is here. So what I do, this A by C may be written as C by A in the denominator. The rest of them are simply numerical values. So packing factor C by A. So in this C by A, I will be substituting 1.63, that is calculated earlier. It was calculated earlier, 7.633. Okay. Now putting all these numerical values, we have to work out. So 2 into 2, 4. 4 gets cancelled here. Then 2 remaining things are 2 into 4 into 3.14 divided by root 3 and 1.633. And it comes to 0.74 or 74%. So the packing factor comes to 74% for a hexagonal close packed structure. Okay, thanks for watching.